In this video, we'll explain Euler's equations of motion, and throughout this video, we will understand Euler's equations of rigid body motion. We will know when a rigid body motion is rotating in a stable manner about its axis, and we will be able to explain the intersections of angular momentum and the energy surfaces and what they have to do with stable rotational motion. And first, we will derive Euler's equations of rigid body motion. And from Newtonian mechanics on rotational motion, in Newton's second law, in terms of external torque and angular momentum, we can write that N, the external torque, is equal to the time change of angular momentum. Now this is in the inertial space fixed frame of reference, and it is more convenient to find these equations in the body fixed frame of reference. So we will transform this in the body fixed frame of reference by transforming it from x, y, z to E1, E2, E3. We could do that by using relation at space so we can do this by this will equal in the body fixed frame reference the time change in the angular momentum L body plus the cross product of the angular velocity times the angular momentum. And we can choose that EI can be the principal axis such that the angular momentum will be equal to the moment of inertia I times the angular velocity. And using these equations of motion, we can write the rigid body equations of motion in the body fixed coordinate system, and it will look like this. It will be N equal to I1 omega 1 dot E1 cap plus I2 omega 2 dot E2 cap plus I3 omega 3 dot E3 cap, and then plus corresponding matrix So this is what the entire equation would look like. And then we can find the components of this equation to find our equations of motion for rigid body motion. And from that, the components of this in the fixed body axis will look like this. N1 equals I1, make it dot 1, minus parentheses I2 minus I3 times omega 2 omega 3, and 2 equals I1 omega 2, or I2 omega 2 dot minus I3 parentheses I3 minus I1 times omega 3 omega 1, and the last one, the N3 I3 omega 3 dot minus parentheses I1 minus I2 times omega 1 times omega 2. And N here is our applied torque, and these three equations will be our Euler's equations for rigid body motion. And in its most general state, we can write this as here, I1 times time differential of omega I, pardon me, now here is our most general form of these three equations that describe Euler's equations of rigid body motion. Now, our next part will be to explain the stability of free motion about a principal axis. And from this, we can consider a body rotating around the z-axis. So we can assume a rectangle like this. So assume some body rotating around its z-axis with a angular velocity omega z. And we can examine this question of stability with two small permutations, rotations about the x and y axis with magnitude omega x and omega y. And where these are relatively much smaller than omega z. And for this problem, the moments of inertia around these axes will be ixx, iyy, izz. And for here, we'll assume that there's no external torque. So then for this problem, our equations of motion will be then 0 is ixx omega x dot minus parentheses iyy minus izz times omega y omega z. 0 equals iyy omega y dot minus parentheses izz is ixx times omega z times omega x, and our last one will be 0 equals izz omega z dot minus ixx minus iyy times omega x and omega y. And from here, we can see that this last equation, with omega x and omega y being very small, that this will come out to be omega z will equal a constant equal to just omega. And then from this, and knowing this, we can differentiate these two equations with time and substitute this in to obtain our main equation, which will look something like this. You could do it for Now the solution to either of these equations, either of these differential equations, can be written as omega x of t equals b e to the square root at plus c e to the negative square root at. Now from here, we can see that if a is positive, there will be an exponential divergence, which will result from the small perturbation that we had in omega x, and omega x will increase without bound, and the motion will be unstable. So if a is positive, our motion is unstable. Now, from here, if a is negative, then omega x will result in oscillatory motion, and our motion is stable. Now, how do we know this? We can examine a then by using this equation to find out what exactly makes a positive or negative. We can do this by examining this equation. Now it's just relating a with our different moments of inertia. Now we can see that if a would be positive, then our moment of inertia, IZZ, will be intermediate of IYY and IZZ, or we can write that as shown here. IZZ will be in between IXX and IYY, either way. Either greater than IYY and less than IXX, or greater than IXX and less than IYY. Now from here, we can see that I, or A, would be positive, and motion would be unstable. Now, we could also see that if our rotation is around a maximum or minimum moment of inertia, A will then be negative and our motion is stable. So in summary, we have that unstable motion. Let me erase this so we can get some more room. Unstable motion will occur about the axis with unstable motion will occur about the axis with the intermediate moment. And we can see that stable motion we can see stable motion will occur about the axis with the highest or lowest moment. And visual representation of This relationship can be seen in the video that is linked right below this video. And now, for our last part, we will explain the relationship between the energy ellipsoid and angular momentum and see how that will affect stable rotational motion. Now, for this first part, we will imagine a sphere with an ellipsoid intersecting it in the middle. With our axes, H3, H2, and H1, and then a circle that has the ellipsoid all the way inside of it. The entire ellipsoid is perfectly inside of the circle with our axes being the same. Now we can see in this one, the intersection between our energy ellipsoid and our sphere of angular momentum in its fixed frame is all across here and on the other side, where I1 is a major axis and I3 is a minimum axis. Now on this one, in our lowest energy ellipsoid, we can see that the intersection between our angular momentum fixed sphere reference and our energy ellipsoid are only at the edges of our energy ellipsoid, here and here. Nice two fixed intersections, instead of in this one, where it's an intermediate ellipsoid, energy ellipsoid, where it's intersecting all across the sphere. And now we will look at another example where we have a much larger ellipsoid with our sphere. So imagine the ellipsoid going around, the sphere is right here, it's intersecting here and around the entire thing. The axis here. And then a much larger ellipsoid here. This is cut in half so we can see the inside of it and our sphere inside. Same axes here. And this is our maximum energy ellipsoid. Before we saw the smaller one where it's perfectly inside our sphere. In this one, the sphere fits inside the energy ellipsoid. And this one is another intermediate one where the top and bottom of our sphere still poke out of our energy ellipsoid. So this is our maximum. And this is another intermediate. And we can see here that our intersection is all across our sphere once again. And here, our intersection is only at the top and the bottom of our sphere. And this, just like in what we explained earlier, in our intermediate energy ellipsoid, this represents unstable motion. And here, at our minimum and our maximum energy ellipsoids, they have perfectly nice intersections which represent stable motion. So in summary, just like we discussed before, in relation to angular momentum and our energy surfaces, intermediate just how we explained before, our angular momentum and our energy surfaces, intermediate axes represent unstable motion, and our maximum and minimum energy ellipsoids or energy surfaces represent stable behavior.